So this is the last lecture. Next time we meet is going to be the exam. This lecture is not going to be part of the exam, so you can relax. This is like a fun topic that I had. Still undecided to do it or not at the end of the lecture, but I'm going to do it. It's reinforcement learning, and I want to give you the basic concepts. So we're not going to use any neural networks today or any high performance computing techniques, but if you want to use them in the future, it's very important you understand how the methodology works for reinforcement learning. So that's why I wanted to do it. It's going to be a very dense, very few concepts, but very important concepts. But there's not going to be a lot of math. It's going to be very much about how it works, what are the important concepts to understand, and what are the problems in making it work, right? So we'll start with the basic definition of reinforcement learning, which starts from before actually reinforcement learning. Learning from experience. I mean, usually what we saw in machine learning, what we did in TensorFlow was mainly supervised learning. We had ground truth, we had a label, like here the cat and the dog, right? You see the picture, you see the label, and you learn to associate the label to the picture. I mean, this is a very simple, way to do reinforcement learning, but it generalized to any other reinforcement learning. The label could be a position, could be a pose in 6 dimensions, it could be any other kind of label, and this could be any piece of data. It doesn't have to be an image, but the important part is that you can associate the ground truth of the label to the environment observation. But when you don't have these labels and you actually learn from experience, like for example, I'll take, because it's fun and because the European Championships have been a few days ago, I'm going to take football as an example for this lecture. If you want to learn how to shoot on goal, basically nobody has labeled for you the image that you see with the door being good and the goal being good and the rest being bad. You try to shoot, that's the idea, and if it goes in, you are good, and if it doesn't go in, you're not good. So basically your actions, these arrows, get labeled bad or good, right? So, and what you do is you learn to optimize the next step of what you're doing, because let's face it, playing football doesn't just concentrate on shooting the ball on goal. You have to get there and you have to get in position to shoot it, right? So how do we do this? I mean, this was easy, right? So you could think, okay, well, let's put a label on each action. This is good, this is bad, and let's learn from that. But there's a few problems with that. This is what we're trying to do, right? Put a reward on the action. If the environment, right, is not labeled, but we can observe it, the environment can tell us if the event was successful or not. This is something that you can do. Without this, we wouldn't have any observation, right? If you just try to figure out how football works without knowing the rules, somebody tells you, well, this is good, this is bad, you have something to go on. But if you don't have anybody that tells you even if you're doing the right thing, then you can't learn it. So this is the limit of it. We assume that we get signals, this is what they're called, from the environment that tell us if an action was good or bad, right? This is what we call a reward. And the reward is given to the immediate action that was taken to get that reward, right? So you shoot on goal, that's a good action. But the previous action, getting to the position where you shoot on goal, well, that's not getting any reward, okay? So, right. So why are we doing this? Important part. Why are we not labeling directly the environment? Can anybody give me an idea why this is the case? Why are we interested in this problem? I mean, we know where the goal is. You can't just label it and say, well, this is good, this is bad. Why are we not doing this? What is this that we miss? Usually when we take this approach, what is that we don't know, or we don't want to know, or we don't want to make the effort to know? It's a model of reality, right? So what we're trying to achieve here is to learn in a model-free environment. We don't know what we're doing. We don't know the rules of football, right? We're just trying to explore what is given to us as options for actions, and then somebody will tell us if we're doing something good. This is a lot easier than actually modeling the whole football and then learning from that. Because if you think about it, here the only thing that I need is some way to interact with the ball, say either in the real environment or with a simulation. And then I need just a score counting, something that tells me if the ball went in the goal or not. There are plenty of games that can do this for us in simulation. Or otherwise, if you have a nice robot, you can try to do it in the real world, right? And explore it there. But you don't need to teach either your agent in the simulation or the robot exactly what to do. You don't need a model for what it's trying to do. So it's very convenient to learn this way, but it's very hard, and we'll see why. The first problem is you are here. The goal is way over there. What are you going to do? And you don't know. Because how do you get from here to the place where you can shoot on goal, let alone score? So the reinforcement learning idea is to use future reward. And do this by basically what you call going steps back from when you score to the place where you were a long time before that, and getting some of that reward also to the steps that led to that, right? So to learn from the sequence of events that led to scoring. That's the basic idea of reinforcement learning. And how do we do that? Well, let's suppose that at the return at the time t plus 100, we actually score a goal. And then we get a reward. Why? Because we scored one goal. So one is the reward. What is the, let's say, let's not call it a reward, but the prize that we want to give to the action before that? We call it discounted return. Well, it's not really one, right? I mean, one was the reward that I got for scoring a goal. Getting in the place where I could score a goal, or should be something less, right? So we actually, because we want to reward immediate action, that have immediate, successful reward for us. We don't want to reward in the same way actions that are very far from the final reward. So we use a discount factor, gamma, that is less than 1. That actually discounts every future action. And the more distance it is, the less important is this reward that I want to bring to the current step in an exponential way. So if this was, for example, 0.1, this would be 0.01, 0.001, and so on. This is usually a lot larger. This is like 0.99, right? But it is an exponential decay. But this way, I can actually get a reward for actions that took a long time ago, like in the midfield that got me to the position where I got just a smaller one, right? So this is the basic structure of reinforcement learning. Can anyone spot a problem with applying this to, for example, football? Any ideas?
You need to be the footballer.
Sorry?
You need to be the footballer to play it.
Yeah, well, okay. Yeah, you need the environment. Right? You need the environment. You need to get somebody to score for you, to count the scores and give you the rewards and log all your actions and so on and so forth. That's fine. We take for granted that we have an agent that is able to move around and shoot the ball. Right? But beside that, football is very, very good example for this.
Maybe you cannot go far to score a goal, so you never get a reward, and then you just like...
Right. How many rewards do you get in an usual football match? What if it's 0-0? Do you get a reward? No. First point, as you said, the reward is substantially delayed, right? So you better have a good gamma. But even if that's the case, the frequency of the reward is very rare. And particularly, it is rare if you don't know what you're doing, right? If you just explore randomly the space, you're never gonna get a signal in the first place. So you can never learn, right? So this is problematic. And it doesn't end there. It doesn't end there. Even if you get a reward, right? What happens is that that reward only propagates back to those actions that led to the score, to scoring. Which means that if you are on the other half of the pitch, let's say this was an action down the left lane, if you are on the right lane, you don't know anything about it. Because there is no generalization here going on, right? You're just looking at, I mean, depending on how you're modeling it, but consider that you model it in like a square of 10 by 10 meters and say if the player was there and the actions would be moving to the next 10 by 10 square meter or kicking the ball, right? So you have simplified model of football, right? But even if you had a model like that, if it was in the next 10 by 10 meter square, you don't know anything about that. Your reward, your return, your discounted return is not propagated there, right? So this is a big problem. Any ideas how to solve this? What could we do? I mean, if you live along this thing, right? But if you think about modeling football, if you want to score a goal, where would you rather be?
Closer to the goal line.
Right, closer to the goal. So what we need to find is to give some value to being in the right place, right? And what does it mean? I mean, there's a concept here of, let's come back to this formula. There's a concept here of return and reward, but before that, at the time t, there's a concept of state. My system, the footballer, has a state. And to get from one state to the next takes an action, right? So right now, we're rewarding actions, right? We're rewarding the action of scoring the goal. But what if we could reward the state? If we could say, well, this state has a better value than that state, because this state is in front of the goal with no defender inside, and I have a very good view of the goal, right? So while the other state is by the sideline and in my part of the pitch, so not really interesting. And that's exactly right. So I went a bit away. So the problem is when you're learning from an episode, right? You only propagate to the particular sequence that we have. We just said it. So that's exactly what we want to do. Instead of just rewarding that episode, we could try and reward. Let's say this is my episode, right? Well, the episode is a sequence of states and action that led to the success or to the failure, but to the reward, to the signal. What can we do with the rest? Okay. So if we could give a value to these states that led up to the reward itself, then maybe we could then use these values to figure out what to do if we're here. What I mean by that is that if we say, okay, this is great, how about we start writing? This action that led me to score as reward 1, right? So let's pass it to the state. Let's say the state as reward 1, because the action had reward 1, right? If I know that this state has reward 1, what I can think of is, look, guys, these states are not so bad. Because if I take an action, I could be here, right? So I could actually try to propagate back my value from the state to the neighbor states, to kind of update the neighbor states whenever I take an action by looking at the state ahead and what I could do there, right? Like I could score a goal, so reward is 1. Now, this is a powerful idea because now I'm not bound to this particular trajectory. I can basically update all my states by looking just one step ahead. And if that step ahead had the luck to be in the episode that went to reward, very good. But otherwise, it could have been updated earlier from one that had a real reward, and then I could now learn from this and go on and propagate my reward through all of the states and not just through the episode itself. Is this clear? Right. So this is a very powerful idea. How can we do this? So this is a particular brand of reinforcement learning, if you want. It's called Q-learning. And what we're trying to do is giving a value to actions and giving a value to states. Now, the value to the state is quite easy. Is the maximum, is the maximum of all the values of all the actions from, this is +1 here, from that state, right? So, sorry about the +1, but basically what I'm looking at, I'm in this state here, okay? And I could do this, or this, or this. My value of the state is basically the maximum value from, say this is 0.5 or 3, because it sounds like a 3, 0.1 and 0.8. Well, the value here is 0.8 because it's the maximum value of all the actions I can take from that state, right? So now, once I have this, this is a recursive definition because this is not an equality, it's not state rule, right? So let's say that I have a value for an action to start with. How do I want to update it? What I want to do is to look ahead, okay? Look at the states that I get from where I am, okay? And look at their value, right? This is the value of the next state. So I look at their value and I take the discounted, again, the discounted value from there. I add it to my return that I just had, and I subtract the current value. Okay, so take it at face value like this, but you can understand where this is coming from. So I took an action, right, that led me to this state. In this state, I can look at what is the value of the state by looking at all the possible actions and taking the maximum one. I add it with a discount factor to my original value, and I remove the current state with a learning rate. So this is a small number, so I kind of reduce the contribution of the old value for that particular action, and I add this part and this part in with a small factor again to move the value of this action a bit towards what I believe is being told me by this experience, and a bit and I remove it a bit from what was my previous belief. Okay, so this is what is similar to what we did in. I'm trying to do this without mathematics. So the idea is that this is a bit similar to what we did when we did neural networks. We're trying to correct our belief of what is good and what is bad based on this experience. So if in this experience my action led me from the state st to the state st+1, I'm going to basically look at what my current return is, right? What the maximum future action is, one step look ahead from all the actions that I have in the next state, by looking at the Q value of those actions that I stored from previous experiences, and I'm going to remove a bit of my previous a priori belief. So this is the correction that I get. It is a correction because I have a learning rate, right? So once I do this, I can update QST and I have my new QST. And if you see this, you'll understand that if I propagate, let's say that this is my state, right? And this is my episode, just moving around the field. This is the goal somewhere, okay? Then you see that this value is going to be propagated from this value. And this value is going to be propagated from this value, right? Because you look ahead and then you update the previous value. So this value, sorry, the value of this action is going to be propagated from the maximum of all these actions basically, and it's going to be written back to the particular value. So you basically go on and propagate backwards at every step that you take. The next time that you have another episode, let's say you start from here, right? You're still learning on your experience, but once you get there, you have already a Q value because you saved it last time. So now this Q value is going to propagate to this particular state, independently of if this particular episode is going to be a reward or not, right? You have another episode and you go around, you encounter an existing Q value. This one is going to propagate back to the episode, to the state before that particular one where I had a Q value. So you're basically, let's say you had a reward here, your reward is going to spread through all of the episodes that encounter existing states that have been valued already, right? So this algorithm works very well in practice. And what we're going to do is we're going to test it. So let's look at a simple example of this. And this is a very, very simple game. What we're going to do is we have a grid 5 by 5, and our objective is to get here, right? So our state is a tuple 0, 0, 4, 4. Our reward is 1 once we get to 4, 4. And it's -1 if we get outside, and it's 0 otherwise, right? So how do we set up our system? And we'll see how we interact with the environment. Now we set up our update group. So first of all, we set up our Q table. Our Q table at the beginning is going to be random, just with some small numbers. So what we do is, a second, that was, yeah, okay, it's 4, yeah. So number of action is 4. We can move north, west, east, or south, okay? We start with a Q table that is a dictionary, basically, where your state is X and Y, so 0, 0, 0, 1, and so on, your position, and your action is from 0 to 3, is basically, so for each of these positions, I have a vector of length 4, where I put some numbers here that are the values. So for example, 0.1, 0.3, -0.5, and so on, 0.3, right? This would be the Q value for this particular state, moving upwards, right, left, or south, this vector. And this is what I'm generating here. I'm just putting 4 random numbers right there of size 4 for this particular tuple, right? So then some plotting, which we'll see later, not in particular, but it is interesting that, that this is, if you've ever not done it, this is how you actually do a plot that is iterative, so that you can draw on the same plot and not just bring multiple images. But not important. How do we update the Q table? Well, this is our update group. This is the important part. So we have to, of course, to pass the existing Q table, the state, the action, the reward, and the next state, alpha and gamma, of course, the learning rate and the discount factor. So current Q table, the max future Q, what is it? Is the maximum of the Q table for the next state. This is what we have in the formula, okay? Then the new Q table is 1 minus alpha times the current Q plus alpha times the reward, which we always have for the current state, plus gamma times the max future Q, right? And this one, 1 minus alpha times current Q, is nothing else that in the update rule, what was split into. You have the current state plus alpha minus the current state, right? So this is 1 minus alpha. Make sense? So it is the weighted average, is another way also to see it, is the weighted average because the current between the current Q table and basically the reward plus the future, the one step ahead look of the future, of the Q in the future, right? So this is how you do it. Now, this is something that when I also learned it from the first time kind of interested me. Why just doing it one step? Why not looking ahead like 4 or 5 steps? It turns out it's not really important because if you're doing one step and you're doing it all over the episodes, you're spreading the value anyway, right? So it's more efficient to do it actually this way. Because you just have a simple update rule and you don't only care about keeping one state at a time. Okay? So this is our update, nothing special. So we save it back to the dictionary where we had it. And then there is our environment. Now, this is our, you call it, you have to be able to play football. Well, this is being able to play football. So this is how we update our state and based on our action. And it could be a simple rule like that. This is a simulation, basically. So what we do is we just enumerate the actions, 0, 1, 2, 3, and we transform the state based on what's going on. So, well, basically we head to the y direction if it's the 0, so it's north, right? East we head to the x direction, south we remove from the y direction, and west we remove from the x direction. And then we check if we're out of bound, we return a terminated state. It's not good, you get out of the field. And if the next state is 4x4, score the goal, we also return the terminated state, but instead of the -1, we return a 1. Okay? And then, if nothing has happened, return no terminated status, reward 0. So nothing has happened. So this is our simulation, quite easy. So how do we train this thing? The training is quite simple as well. Basically, okay, so initialize our plotting, then we define a max number of episodes. We want to stop the training at some point. And what we do here is we just give a maximum number of steps for an episode. Okay, if it doesn't get the reward by the 100th time that it's iterating, you just stop it, truncate it, right? So this is an important trick. So what I'm doing here is that for a number of actions, random actions, for a number of actions, I basically, instead of looking at them at my policy, okay, the Q table, I am just taking a random action. Why am I doing this? Let's say our policy is stuck in some behavior, like for example, it learns that whenever it's in this particular state, it wants to go right. But this is not the right action. But it will never unlearn it because it doesn't have any possibility to go left and see what's happening on the other side. So because of this, it's important to give it always a bit of randomness to make it so that they explore the environment instead of sticking to what it knows. So what we're doing is we are starting with some randomness. At the beginning is just doing random things, right? And then we'll slowly gain the randomness until we are at 0.01. We always give it a 1% chance to do something different, all right? You could start with a lower epsilon, you can start with whatever you want to decay. You can explore these different problems at different parameters, of course, it's an hyperparameter. So if we are in that particular case where random is less than epsilon, then we do a random choice. Otherwise, very simply, we look at the Q table for that particular state and we take the argmax. That's the most valued action, the maximum Q value that we have for any action that's coming from that state, right? So we go and do our step in the environment, so the function that we just saw. We recover the next state, the reward, terminated, truncated is actually ignored. We update the Q table. as we saw before, with the state, action, and reward that we just got in the next state. And if it's terminated, we break. We update our plot, and we update our epsilon. So we have this decay for our epsilon that is basically multiplying by the epsilon decay and taking the maximum between the mean and that particular decaying value. Is it clear? If I always, every step I multiply by a factor, this is an exponential decay. Right? Any questions on this? Scroll. And that's it. And then I start the train. Train my Q table, use initialize, and render true, and max epsilon 1000. I need to do it from outside because otherwise it doesn't render. So let's do it from here. So here I'm plotting the Q values of the state, actually the values of the states, right? So the maximum Q value for any action coming from the state. And as you see, as it learns, it propagates the values basically from the word back to the rest of the states. And you see a gradient form. What this means is that the actions will always know that it's good to go in this direction, in this direction, in this direction, instead of the other direction, right? So this is I'm just running it again. This is a very convenient way to do this. We didn't know the rules. We didn't tell it that the goal was at the bottom right, but it learned it automatically. It learned how to model the value of my state. Space, right? Because again, not only of the action space, the state space, because the action space is a lot denser. You have a lot more actions that you have states. Because you have, for each state, you have a branching to all the neighbors, which could, in this case, are 4, but it could be a lot more. And valuing every action is a lot more complicated than valuing every state, right? So it's very convenient, and it starts learning to solve the problem very quickly. I didn't plot this, but so you can see that this is a lot more efficient than what comes below. All right, so next example that I want to go through with you is a bit more complex. And first I'm going to show it to you. Then we're going to go through it. So what is this? This is an environment from OpenAI Gyms that is the card pole environment. And it's trying to learn how to keep the pole upright. Right? So this is not a discrete problem. This is a continuous problem. Right? You have to model basically all possible angles, states, velocities, and so on. Right? Now, the Q table is a discrete system. You have to assign a value to an action. No, you don't have a distribution of action. You have a value and an action, and so on. So, by the way, you didn't learn? That's interesting. Well, it wasn't so efficient. We are going to check the parameters again. But the point is, to do this, yeah, you didn't learn, and we see this from here. To do this, you have to somehow discretize your state and your actions. And usually it's not a bad idea. Oh yeah, now it should have learned. So what's going on here is that we have 4 environment parameters. The card position, card velocity, the card angle, and the velocity of the pole, right? And instead of looking into the exact value of this, we're going to create beans. Okay, so we're going to take 20 of such beans for each of the dimensions. So we'll have 20 to the 4th power possible states. And we're going to learn if for any of the states, it's more convenient to go left or to go right. That's all we're going to do. That's all the input we want. So we have less actions, we have a lot more states. Right? And what we're going to do is to learn this Q table, but also we're going to try to understand what's going on with the Q table. And we're going to look at this kind of particular plots. So this was the Q table as it started. Let's see. Here I took the average Q value for actions left and action right, and the average taking without changing the pole angle, right? For each pole angle, okay, I took the average of all the pole velocity, cart positions, and so on, and the Q value of this particular action. Why? Because I'm interested to see if it learned to associate higher value to positions that are near zero in the pole angle, and lower value to positions that are deviating from the zero position, right? So you could do this also with velocity or with the cart position. Basically, the velocity equals zero and the cart position equal the middle should be the highest valued place, right? Is it clear why? I mean, if the game is basically that if you are more than 20 degrees or 12 degrees, I don't remember, out of the vertical position, the game ends and you get a -1 reward. If you are perfectly aligned, you're good. And you get a 1 reward each time you stay up there, right? So the longer you can stay up there, the better it is. Once it learns something like this. And you can see that it basically learns to stay in the middle. Not only gives higher values to the middle, but you can see that outside from the zero, and there is a slight deviation here, which is probably the problem that we saw before. Outside of the zero, the left action is greater than the right action for negative angles and vice versa. So it really learns that it wants to compensate to get back to the zero, right? You could do the same with the position, and you would get a similar curve. Or you could do a multi-dimensional plot and see all sort of nice things, but not really easy to then visualize. So how do we implement something like this? First of all, we don't have to care about the environment because somebody did it for us. And if you want to explore a bit this particular games, there's more of them. There is this library gym that you can use, and you then initialize them like this. So it's very simple. You just initialize the gym, and what you do is you use. Remember, we were using our step function that we created with the if for all the actions. Where in this case, you can use the gym to return to you next state, the reward, terminate the truncator, and some information. Right? So quite easy. What is not easy is you have to take into account all the discretization of the states and be sure that you deal with that correctly. So I'm just going to go through this quickly because this is not as interesting as actually looking into the plots and looking into how the parameter change the behavior of the system. But so that you don't look at a bunch of code without understanding what's going on, I'm going to go through one. So this is the same as we did before. We're just randomizing the Q table the first time around. Here we have the beam counts +1, and we assign random values to a 2 vector for each state. Okay? The 2 vector is left and right moments. The plot, oops, no. Start it again. All right, so the plot of the Q table is just taking the average over certain over all dimension except for where it is. Right, so we iterate over all of them and then we sum up the averages and then we plot it. It's not really something that, because we divide by the counts, that's all. The update of the Q table is exactly the same function as before. Nothing has changed, so we take the Q and Q, multiply by y minus the learning rate, and we add with the learning rate the reward and the future Q. And we update the Q table. The training is also very similar. The only thing that we have to take care is that the environment is giving us a continuous state, and so we have to discretize it. So this discretization is just a function that I have up here that is just going to digitize the value according to the bins. So using this very useful function from NumPy, you can read in the documentation, right? And that's it. That's pretty much what this is about, okay? So what we were looking at before is this particular process. So first I'm going to simulate with 10 episodes the random Q table that I have, right? I'm also learning, but in the first 10 episodes, I'm not really doing much. Episode 0 is, yeah, it's okay. Because this is really simulating it. So, and anyway, the Q table is random, so the epsilon doesn't do much because it was random anyway. Then I've stopped the rendering because I want to actually do some learning, and the rendering it will slow down the learning a lot. Learning 10,000 episodes, and then I'm simulating again 10 episodes with epsilon set to 0, important, because otherwise you're simulating a random action given by the epsilon, right? And mean epsilon set to 0. So I can check what is my now learned Q table doing in the real problem, right? And then I'm just plotting again the Q table. Let's run it again because the first time around wasn't actually great. So first episode is the first agent is basically fading. You see it's going inclined up to 12 degrees and stopping. Now it's what is it? Now it's learning. The epsilon is going down. So it's going down to 0.01 by 5,000 episodes, and then it's learning 1,000 episodes every time, which is quite fast. You see, it's the environment. You can use it on a regular computer. You can train for something like this and experiment around. This, of course, is a very simple simulation, right? But nevertheless, if you want to learn reinforcement learning, is a great platform to learn it. So now
something while it's working.
Sorry? Yeah.
May I ask something? So when we are discretizing, we take the position of the card pole and then just assign it to the bin that it is inside, right? The value that it gets is also assigned to that bin it was inside.
So when you're discretizing, you're taking a continuous number. So let's say our position is -2 to 2, okay? Then I decided this, so -2, -1, 0, 1, 2. These are the limits. There is a unit here, a unit here, a unit here, and a unit here. And I want to divide it in 20 bins. So these are 4, 8, and so on. Let's say I want to divide it in 8, okay, because I cannot write the rest of the 20. So what I'm doing is assigning a value here that is 0, 1 that is here, 1, 2, 3, 4, 5, 6, 7. And then these are the digits. That's why it's called digitize.
We also discretize the velocities, right?
We discretize everything.
Okay.
And everything in 20 bins.
Yes.
So what's happening is that if the value is between -2 and -1.5, okay, in this range, then my discretized value is 0. It's a digit. I don't care if there's any relationship between the two. It's just a digit. It's a representation. And so on. If it's between -1.5 and -1, then it's 1, and so on. So what I have then is I have a grid where I have you know, the angle here, the angular velocity here, and this is like 0, 0, and I have 0, 1, 1, 0, and so on. I have this grid. Then I have another dimension for the speed, linear speed, and another dimension, I don't have 4-dimensional board, but another dimension for the linear position. Okay, this basically tuple, like 0, 5, 3, 8, is going to give me the state of the system in a discrete manner, right? And the Q table then is just, for this, is going to be another tuple, which is like 0.7, 1.3, which is, this is the left action, this is the right action, and I'm going to take the right action because it's 1.3. Okay, so this is how we basically create the Q table.
Yeah, my question was, there's also like this option to linearly interpolate the closest, let's say, two bins. And so what do you think would be the disadvantage of like doing this bin discretization instead of this?
What do you mean? I mean, we are linearly interpolating. I mean, we're not interpolating, sorry. We are taking the nearest neighbor in specific particular value.
I get that.
So this is basically the same as saying, okay, interpolating means that instead of taking the value of the Q table for the second bin, or the value of the Q table for the first bin, you take the weighted average between the two, and then you take that. Yes, you could do that. I don't know, I didn't try. Does it help in this particular case? So maybe, but I think usually it won't. I mean, the point is that the states are very well defined. If you are inclined to the right or to the left, there's usually a clear best decision, which is getting the pole upright again, right? So moving to compensate that particular one. So where it might help is where you have basically a combination of velocity, angular velocity, and angular position that are really required to use a kind of fine-tuned decision around that particular value. So in transition states. So if you have a states where, you know, the cart is a little bit inclined, but it's also traveling, right? And therefore, but there's also have an angular velocity that you pulling up right already. So the question that you're asking is, do I push left and maybe overshoot? Or do I push right and like don't arrive at the top, right? Because I'm actually compensating the angular velocity that's pulling me up. In this case, interpolating might give you an advantage by just, you know, interpolating properly between two states that have a definite decision, but in between you don't know. So yes, that could be an idea. You could try. I mean, the code is quite simple.
The problem is I also had a homework for like this, do you know the mountain car problem?
No.
So like basically the car cannot go, so like there's like this mountain and you cannot just go right and access there. So you need to first go back a little bit and then you need to go.
Okay.
And my problem is that in that question, when I did the normal like bin assigning, I couldn't manage to get it done. But then when I implemented the like linear interpolation, it worked, and I still have no idea why it works. And like the first option doesn't work because like the bin assigning also makes sense in this question, and it doesn't have this transition points as you said. So I wonder like why it could have been happening.
Maybe the discretization wasn't finer enough. I mean, we need to look into the details, of course, to understand why it didn't work. But yeah, I mean, interpolating can give you a bit of an advantage if your bin association was not fine enough and you have some transitioning that happen where you need to take the right decision.
Yeah.
But I have no chance to guess why it didn't work from but what we can see is that this time around it worked, because for all the simulations that we did, it took actually almost all the time to 500 steps. Sometimes it stopped before, but he actually got a very good run. If we look at the examples at the beginning, it was didn't never manage to get over, well, 79, that was a good run, but otherwise never over 50 or something like that. So again, let's run it again, just I'm staring at the, I don't know what's doing here. Staring at the examples, so see when it starts again. In the meantime, we can look at the tables. And again, you see the Q table in the beginning is pretty much random, but when it arrives at the end of the training, again, it has a very clear structure where the middle angles are preferred, and depending on the side you are, one of the two actions is preferred over the other. And this is why it actually has a chance to work. Where is it? 9,000. So now it should again. So you see, now it's actually keeping this in equilibrium, and every action is actually good effect. Right. And again, this is an incredibly simple algorithm that we implemented. You can see the plot. Every plus is a move to the right, every minus is a move to the left. So there is no like regular things like it moving one time to the right, one time to the left. It's actually reacting to the state pretty in complex way, right? Let's put it this way. Again, it's a value table. Discretized value table, left or right choice. But it solves a very continuous and dynamic problem. Okay, this is a simple problem. You can solve it with the control theory, you can solve it anywhere you want. But I think it shows you how powerful is this method of dealing with learning from the environment. Okay. Just observe it for a second, and then any question in between? If you like this stuff, I encourage you to play around with the gym. It's really cool. To build something like this from scratch, it takes you days. I mean, this is just, you install it, you play it around, and it's fantastic. All right, so this is actually all I wanted to tell you for today, because I don't want to start with more complex methods. I think this is enough for a first deep into reinforcement learning. Because otherwise we'll have to take another hour to just explain theory. All right, so if that's nothing, then I'll stop here the lecture. I hope to see you all on the 12th of August. And if I manage to record it.